So the purpose of bivariate linear regression is to predict one variable from another variable using a straight line to do so. So if two variables are correlated, you can use one to predict the other. That prediction is called bivariate linear regression analysis. So for example, SAT scores are correlated with first-year college GPAs, so college admissions uses SAT scores to predict the likelihood that an applicant will succeed in college. It's bivariate linear regression. It has nothing to do with Freud, by the way. So how well the prediction works is based on the strength of the variable's correlation. Stronger correlation equals higher R squared equals better at predicting each other. So for example, if height and weight are correlated, you can use linear regression to predict someone's weight from knowing their height. And this is how they do it at the state fair. When that person bets you $5, they can guess your weight. So linear regression allows us to predict the value of a y from the value of x, or vice versa. And remember that prediction does not equal causation. This is all based on correlation, so the same rule applies. So bivariate linear regression is used to estimate a straight line that can be used to predict the variables from each other. That line of best fit that you've been adding in scatterplots, it is this bivariate regression line. That's what it is, same thing. So that line and that plot, current salary, beginning salary, that we've been having SPSS put in our scatterplots, that's a regression line. It's a bivariate line of best fit. So that line can be represented by this equation, y prime equals bx plus a, where y is the predicted score. Okay, it's called the DV in SPSS. The thing you're trying to predict is y. B is the slope. That's the change in y for a 1-unit change in x. So it's the rise over run from back in the day. X is the score for the predictor variable, so it's the IV in SPSS. That's the one you're using to predict y, so the x variable and the y variable. A is just where that line crosses the y-intercept. So if it crosses at 0, it's 0. If it crosses at 100, it's 100. That's all A is. So that equation, y equals bx plus a, SPSS will estimate b and a for you. So it turns out this is the same thing from algebra back in high school. Y equals mx plus b. They just swapped out some letters because they like to do that to us. So which variable below do you think would be the best predictor of employees' current monthly salaries? Here's a correlation matrix. First column there is current monthly salary. Which variable do you think would be the best predictor? Well, it's going to be the one with the strongest correlation, right? So points negative 0.14, 0.88, and 0.661. It's going to be the 0.88. That variable, which is beginning salary, is going to be the best predictor of current salary. So recall that the squared correlation coefficient tells you the proportion of variability in one variable that can be predicted by the other. So in this example, 0.88 squared is about 70 times 100, is 77% of the variability. So knowing someone's beginning salary, you can predict 77% of the variability and what their current salary is just by knowing where they started. So first step, does the relationship between beginning and current monthly salary appear to be linear? That is it appropriate for linear regression? There it is. Does that look like a straight line does a pretty good job? Yeah, pretty good, right? You know, it goes through the center of most of the dots. So when you're drawing scatter plots for regression, it's different than earlier in the week correlation. It matters which one's on the y-axis. You have to put the variable you want to predict on the y-axis, the up and down one. So that always goes on the vertical or the y-axis. So in this case, we're predicting current salary from beginning salary. The predictor, that is the other variable you're using to predict, the predictor, it goes on the x-axis. So we're using beginning salary to predict current salary. Something called the standard error of estimate. The standard error of estimate in bivariate linear regression indicates on average, how much the actual y values will differ from those you predict from your regression line, that is y prime. So how much, for example, someone's actual salaries differ from what you predict based on your model knowing their beginning salary. So higher R squared equals better prediction means you'll have a lower standard error of estimate. Your predictions are better is really all this means, okay? Less error in your predictions. So the standard error of estimate is the standard deviation of the regression line. It's on average how crappy our prediction is. On average, how much our predictions differ from average. The line is the average in this case. So it turns out if you take the standard error of estimate and you subtract 1 and add 1 to someone's estimate, it's kind of like a z-score. You know that someone's actual score will be within that interval. That's y predicted plus and minus 1 standard of estimate about 68% of the time. Kind of like the mean plus and minus 1 standard deviation gives you 68% of scores in a normally distributed for a normally distributed variable. Same thing here. If it's normally distributed, their predicted score plus and minus 1 standard of estimate will contain their real score 68% of the time. Same thing if you add plus and subtract and add 2 standard errors of estimate to their predicted score, you get an interval where 95% of the time you would predict their score would be in there. And then finally, the third one as well. Their predicted score plus and minus 3 standard errors of estimate will give you a range where 99% of the time their true score will be within that range, like their true actual salary. So it's sort of relationship between z-scores and bivariate linear regression. So there are these things called assumptions. I think this is the first time we've talked about them. These are things that should be true for this to work. So for your bivariate linear regression to give you good results. 1, linearity. The 2 variables should have a linear relationship. That should not be a shocker. This is based on correlation. So 2 variables should have, you're using a straight line to predict the relationship between one and the other. So a straight line should do a good job of representing that relationship. So normality, it's a new one. Normality is that the scores are approximately normally distributed. So both variables are approximately normally distributed. So again, how would we test this? They have skewness values that are less than 2 absolute value. So the one exception is dichotomous variables. You can use dichotomous variables in regression just like you could in correlation, but only if they've got 2 levels. Okay, so nominal variables with 2 levels you can use. Ones that are 3 or more cannot use this. So this third one is 10-cent word of the night, homoscedasticity. This is when your prediction of your y values is just as good across all possible x values. So it's equally good or equally bad or equally crappy. For any given x value, you're about as wrong as for any other x value. That's called homoscedasticity. So if that's not the case, you have heteroscedasticity. There's the other 10-cent word for the night, which is bad. So you want homoscedasticity because there's only 1 standard error of estimate. So you want a single error number or how bad your prediction is to work for all values of the line. So here we have an example of a relationship between x and y. There's a line in there. You can see that the dots, which are people's true values for whatever x and y are not exactly on the line. This is not a perfect correlation. The extent to which they differ from that line is your standard error of estimate. And for all values of x, they're kind of above and below the line about the same, right? That's homoscedasticity on the left. That's good. On the right, we have heteroscedasticity. Heteroscedasticity is when your prediction is not this equally bad for all levels of x. And so as you can see, the dots are pretty close to the line, meaning their actual values differ not that much from what we would predict, which is on the line for low values of x. But when you get to high values of x, the actual values differ way more from the line. This is heteroscedasticity. This is bad. So you want the one on the left. So good news, SPSS does most of this for us. So find this on the SPSS regression output. We got to fill in that y equals mx plus b line. So here's the first thing we get is the variables that were entered into the equation. It entered beginning salary to predict current salary. Down here, current salary is the DV. Model 1 has a predictor of beginning salary. So in the next little table you get in SPSS is called model summary, and there's some stuff in there. I've crossed out one because it totally confuses people. So Make sure you ignore adjusted R when you see it. But there is R squared, and standard error of estimate. Find the standard error of estimate. Well, what do you know? It's the thing called standard error of estimate. So on average, our prediction, what we would guess someone's salary is about $3,246.14 wrong. Up or down. Standard error. Okay? We're plus or minus that is what we'd expect our prediction to be. How about R squared? Where's that on here? Again, it's where it says R squared. So 0.775, that is our correlation coefficient squared. It was 0.88, I think. Yeah, there it is, 0.88, because R's on here as well. It was 0.775, multiply it by 100, you get 77.5% of the variability employees' current monthly salaries can be predicted by knowing what they started at. It's pretty good. All right, so now what we have to do is replace B and A in the general regression equation with numbers that SPSS gives us to build the full equation for predicting someone's current salary from their beginning salary. There's the general form from earlier. Y equals bx plus A. We have to find B, that is the slope, and we have to find A, the y-intercept, in the SPSS output. So there's the coefficients table. B is the slope. It's in the table row that's got the name of the predictor. So what is our predictor here? Our predictor is beginning salary, where someone started at the company. We're predicting current salary, which it shows below this table. So which row says beginning salary? That one. See that 1.909? That's B. So here, I've taken 1.91 or 1.909 and rounded it to 1.91, filled it in. That's B up above. I've replaced it with 1.91. All right, so now we need A. So A at the end there is the y-intercept. It's where the line goes through the up and down axis. So where's that in the table? It's in the line called constant, 771.282. Fill that in where B was above, and you've got your full regression equation filled out. Someone's current salary is equal to 1.91 times their starting salary, and then you add $771.28 to it. That'll give you someone's predicted current salary. Once you've got that equation completed, you can put in any X value, that is any beginning salary, and you get a Y value out. What do we think they make now based on where they started? So there's that same equation from the prior page. And let's say that someone's beginning salary was $4,000. We would predict by filling it in where X says beginning salary there, 191 times 4,000, do that, plus 771.28, we would predict that person currently earns $8,407.28. If they started at 6,000, fill it in the equation, do the math, we'd predict someone who starts at 6,000, what they make now, $12,225.28. How about if someone started at 15,000? They start at 15,000, fill it in the equation above. We're just filling in the X value and getting the blue Y. If you start at 15,000, we predict you make $29,406.28. That's what we predict. This is all there is to this bivariate linear regression. So you can also go backwards. You can solve for an X given what someone's predicted salary is. So it's just a little bit of algebra. So the formula flipped around for predicting someone's beginning salary based on what we thought they currently earn is just their current salary minus A, and then that thing's divided by B. That gives you their current salary. It's just flipping around the equation. So beginning salary of someone who makes 35,000, flip it around. We predict they make, so hint, same B, same A, $17,930 is where they started at the company. So if they have their beginning salary was $17,930.18 for a person who we predict currently earns $35,000. So you will be doing an APA write-up of your regression analysis that you do for your homework problem using a template that I provide up on Canvas. Make sure you use the template, write over it, change things so that it works for yours. Do not do this from scratch. But I want to show you where some of the things come that are in that APA write-up from your SPSS output. So there's a table called Table 3, and it's a summary table of your regression analysis. And the stuff that goes in there comes from two tables, the coefficients table and the model summary table we talked about earlier. So that first row, beginning salary, you need B's, betas, R, and R squared. And below the table, you need your standard error of estimate. So where does that stuff come from? Well, the B value for beginning salary comes from the column called B in coefficients. The constant, that is your y-intercept, comes from the B column where it says constant. So note that they are starred, or not starred, but in this case they're both starred. That means they're statistically significant. Where does that come from? Well, that comes from the sig column. Sig is less than 0.05. You put a little asterisk next to the number. And note below the table there's p less than 0.05. That's what the star means. So the beta comes from a column called standard coefficients beta. So that only exists for the predictor. R comes from the column called R in the model summary, and R squared comes from the R squared column. You round it to 2 decimal points using Excel rules again, so it's 0.78. And then finally, don't forget the standard error of estimate below the table comes from the model summary where it says standard error of estimate. That's where all that stuff comes from. So the APA template also has in the middle of a sentence this thing called an F test, which is an ANOVA test. I also, we're going to talk about ANOVA in the future, but for now I just need to show you where does this stuff come from on your SPSS output so you could fill it in. So there's a sentence in the APA write-up, the linear model resulting from regression analysis was statistically significant. It's presented in table 3, comma, F, blah, blah, blah. Well, where does all this stuff come from? Well, there's a table on the SPSS output called ANOVA, and it is the numbers that go into this. So that F1 and 472, then the F value, then P less than 0.05. So the 1 and 472 come from this table right here called ANOVA. 1 is the value for degrees of freedom up top. 472 is the value for degrees of freedom on the bottom. 1 and 472. The F value, that 166.12, is from where it says F. So you just round that to 2 decimals and boom, put it in there. Sig, if the sig value is less than 0.05, you put P less than 0.05. So that's where that information comes from. If you have any problems, post your questions in the discussion. Otherwise, good luck.